When a global crisis hits, the traditional humanitarian supply chain often freezes. The relief network stalls at the border, and the very supplies meant to save lives sit motionless in the rain. We already produce enough agricultural biomass to feed the population, but our distribution is fragile. Centralized funding models prioritize just-in-time efficiency to maximize returns, which leaves no financial buffer for regional surplus. When a crisis breaks the standard logistics routes, there is no localized capital to pivot or push through the physical bottlenecks. The neo-pioneer movement approaches this failure as a solvable engineering problem. As their manifesto argues, science provides the mechanism to bypass these bottlenecks. By applying strict biophysics and extreme decentralization, communities can build an alternative supply chain. To maintain delivery during a collapse, you have to step away from fragile central authorities. The solution is engineering a self-replicating, autonomous network, one that grows, preserves, and distributes its own resources. The foundation of this system is planted in specific subtropical corridors around the world, USDA Zones 9A through 10B. We target locations like Portugal's Alentejo Basin for two exact metrics: high solar irradiance and the water security provided by extensive reservoir systems. Across 10 of these global sites, we deploy 110 starter nodes. These farms are arranged into a 14-mile hexagonal bioeconomic cluster, maximizing internal logistics. At 24 months, this geometry expands. Mature nodes generate cash flow and starter stock to spawn daughter nodes, rapidly multiplying to 880 operational nodes globally by year 6. Because the physical farms generate the capital and biological material required to expand, the network removes the need for outside investment. It scales through its own surplus. At that year 6 milestone, the scale of production reaches industrial levels. The global network yields 28.5 million pounds of fresh produce and fish annually, while simultaneously refining over 200,000 gallons of B100 biofuel to power its own operations. But moving highly perishable fresh food across the planet during a crisis is nearly impossible. To solve this, each farm node is equipped with on-site modular cleanrooms. Inside these processing hubs, the surplus biomass goes through a rigorous preservation cycle. The fresh food is converted into densely packed, vacuum-sealed foil bricks engineered for 10 to 25 years of shelf life. By removing the water weight and locking the nutrients in sterile packaging, local harvests are upgraded into permanent, deployable assets that will survive transit into any environment. Moving millions of pounds of preserved rations requires industrial infrastructure. By year 6, the network generates $150 million in annual net profit, which it uses to fund direct intermodal links to existing heavy-haul electrified freight rail spines. These corridors connect inland farm nodes directly to deep-water maritime hubs. In Brazil, a dedicated freight link transports the rations from the São Paulo interior to the high-capacity loading terminals at the Port of Santos. This exact architecture is mirrored across the planet to ensure logistical redundancy. In Chile, an electrified intermodal line carries the assets from the Central Valley directly to the water at the Port of San Antonio. The same pattern repeats in North Africa, with a high-speed freight spine linking Morocco's Souss Massa Basin straight into the coastal logistics hub at Agadir. These rail lines act as physical arteries. They are the essential mechanism that turns isolated inland agricultural projects into connected export hubs, moving vast quantities of supplies at high speeds. Once those rations hit the deep water ports, the network initiates the final stage of deployment, financed entirely by its own internal capital pool. The final link in the chain is a dedicated zero-emission relief fleet. These heavy-lift electric cargo ships operate alongside giant maritime water harvesters, moving directly toward the impacted zones. Because these ships carry their own fuel, purified water, and decades of preserved rations, they operate outside traditional constraints. They bypass stalled land borders and deliver heavy resources straight to the crisis. From a seed planted in a subtropical basin, to a vacuum-sealed ration block, to the deck of an electric supply ship. The biological mesh yields the product, the rail moves it, and the fleet provides a direct logistical path to those in need, forming an autonomous pipeline that functions when the rest of the world stops.